only less blood can enter the capillaries, automatically this decreases GFR. All constrictions decrease renal blood flow. Before, the substance that commonly does this is angiotensin 2, efferent arteriole constrictor. You get a what is GFR? GFR initially increases followed by a later decrease. As I told you, all constrictions decreases renal blood. If you open the gate more in the beginning itself, automatically more amount of blood now go into this glomerular capillaries. Automatically this maneuver increases GFR. All dilations increases renal blood flow. Simple. Dilating efferent arteriole, more blood is GFR. Dilatation arteriole, AC inhibitors. Now look into this diagram. This is our efferent arteriole. If you dilate its caliber more, efferent, this blood will quickly pass into the efferent side. From the glomerular capillaries, because of dilation of efferent arteriole, blood will quickly move into the efferent arteriole. The blood stays very less time in our capillaries. This maneuver. Because the efferent arteriole, less time it stays efferent arteriole, effect on GFR, decrease in GFR. These four maneuvers are very important. Constriction of efferent and efferent arteriole, dilations of efferent and efferent arteriole. What is going to be the effect on GFR and renal blood flow? You need to be very thorough. Alright guys, another way of modifying our GFR is through mesangial cells. What are these mesangial cells, sir? Where they are? These mesangial cells surround glomerular capillary. These mesangial cells are contractile. These mesangial cells surround glomerular capillaries, they are contractile. By any chance, if you cause mesangial cell contraction, this mesangial cell is now going to compress glomerular capillaries. When you compress glomerular capillaries, less blood will enter into this capillary. This maneuver decreases GFR. Mesangial cell contraction compresses capillaries, less blood will enter into this capillaries, decreases GFR. Which agents cause mesangial cell contraction? Endothelin, angiotensin 2, all vasoconstrictors cause mesangial cell contraction. The opposite maneuver, mesangial cell relaxation, allows glomerular capillary to expand. Now glomerular capillaries expansion means it can get filled with the blood, and this maneuver increases GFR. Mesangial contraction decreases GFR, mesangial relaxation increases GFR. This mesangial relaxation is usually done by nitric oxide and atrial natriuretic peptide. Mesangial cell contraction decreases GFR. Mesangial cell relaxation increases GFR. Now, with that important note from GFR, let's focus on now the renal blood flow. How much is the kidney blood flow, sir? Kidney receives around 1.2 to 1.3 liters of blood, which is roughly around 23% of cardiac output. On an average, we take as 1250 ml per minute. Renal blood flow, 23% of cardiac output. Even though it is the total blood flow, but what is actually filtered? It is the plasma that is filtered. So the best thing to estimate is renal plasma flow. This renal plasma is the one that is getting filtered. This renal plasma is 25% of our total. 25% of around. We all know GFR 125 ml per minute. There is one important ratio we are going to formulate now that is called the filtration fraction. It is the ratio of GFR to renal plasma flow. So filtration fraction equals GFR divided by renal plasma flow. We know GFR is 125 ml per minute. Renal plasma flow. Filtration fraction for GFR you need inulin. For renal plasma flow, remember P for P. Renal plasma flow estimated with the help of para-aminohippuric acid. So substances needed to estimate filtration fraction are inulin and para-aminohippuric acid. Concept of filtration fraction very important. Now, we are discussing a lot about filtration. Following filtration, the substances need to get reabsorbed. That important reabsorption happens where? To know that, we have to understand the parts of nephron. This is actually our glomerular capillaries. Following fluid filtration, majority of the fluid enter into this convolution we call proximal collected tubule. After this proximal collected tubule, the fluid will go into descending loop of Henle, then ascending loop of Henle, then it will come to the distal convoluted tubule, and finally to our collecting ducts. So, PCT, descending loop of Henle, ascending loop of Henle, DCT, and collecting ducts. First, let's focus on proximal convoluted tubule. This is the segment PCT exclusively known for maximum reabsorption capacity. Maximum reabsorption of substances always happens in PCT. A typical PCT cell, look very carefully. Its surface will have lot of finger-like projection like this. Inside this PCT, you see lot of mitochondria. PCT cell has got a finger-like projection and whole lot of mitochondria inside them. Why, sir? Because this small finger-like projection are called the brush border. They increases the surface area for reabsorption. PCT is the site of maximum reabsorption. And the mitochondria, why? Because majority of the transport process here are active transport processes that requires energy in the form of ATP. This ATP synthesis happens in mitochondria. That is why PCT cell, more number of mitochondria to give energy source ATP to carry out this active transport processes. Site of maximum reabsorption, PCT. What fraction of substances are reabsorbed here, sir? Remember guys, close to 70% reabsorption for sodium, water, potassium, urea, calcium. Close to 70%, 2/3 of the filtered fluid is reabsorbed here. Around 70% of sodium, water, potassium, urea, calcium. 80% of phosphate and bicarbonate. Out of this, bicarbonate is very important. 80% of bicarbonate reabsorption in PCT. 100% whatever filtered will be completely reabsorbed for glucose and amino acids. Remember glucose reabsorption 100% in PCT with the help of a very important channel protein. Which channel protein? Can you answer me? Glucose reabsorption in PCT. Which channel protein? Excellent. Sodium glucose cotransporter, the isoform is 2. Very important graph, guys. SGLT2. A classical example for a secondary active transport process. This process shows the phenomenon of saturation kinetics, which means very simple. Glucose will not be indefinitely keep on getting reabsorbed. After some point of time, this process shows saturation because availability of this carrier protein is limited. Once all the carrier protein are used, you need time to synthesize new carrier proteins. Then only the process will resume. Two important key parameters need 375 milligram per minute. Kidney can maximally transport 375 milligram glucose per minute. We call this parameter as transport maximum for glucose. This corresponds to a plasma glucose. A plasma glucose value of 180 milligram per deciliter. This 180 milligram per deciliter is called renal threshold for glucose. What is the meaning of renal threshold for glucose, sir? If the plasma glucose becomes more than 180 milligram per deciliter, glucose will be excess. We call that phenomenon as renal glycosylator. What is the meaning of renal threshold, sir? If plasma glucose value exceeds 180 milligram per deciliter, all the remaining glucose, excess glucose will be excreted. We call that phenomenon as renal glycosuria. So PCT, site of maximum reabsorption, 100% reabsorption is there for glucose. Remember this important point also, the nature of fluid in PCT is always isotonic. Because equal amount of water and sodium are reabsorbed, the nature of a fluid in PCT is isotonic, having an osmolarity of around 300 milliosmoles. The nature of fluid in PCT is isotonic. So from PCT, next the fluid will go into the loop of Henle, exclusively important for concentration of urine. Very important. We have descending loop of Henle, we have ascending loop of Henle. There are two important tubes here. The fluid movement is opposite in both of them. Two tubes very close to each other. The direction of fluid movement is opposite to each other. This system is called a countercurrent system. You see this type of system in kidneys. Not only kidneys, you can also see this in GI tract. You can also see this in testis. This type of countercurrent system can be found in kidneys, GI tract, testis. These are the few examples. Now here in kidney, we have descending loop of Henle and ascending loop of Henle. As I told you, the fluid coming from the PCT is isotonic 300. Now it comes to our loop of Henle, descending loop of Henle. This descending loop of Henle is permeable to water, but impermeable to solutes like sodium. So what can actually move out? Water can move out. What cannot move out? Sodium cannot move out. You are throwing water out, selectively placing lot of sodium ions inside, thereby this segment undergoes concentration. 300 becomes 600, 600 is concentrated to 900, maximum most concentration at the tip of loop of Henle, 1200 osmoles. Why is this capability, sir? Descending loop of Henle is permeable only to water, but impermeable to solutes like sodium. Sodium is staying inside, making this segment concentrated. That is why this segment is called as, remember guys, concentrating segment of nephron. Which is segment? Descending loop of Henle. So the fluid is concentrated here. Now the fluid will come to the ascending loop of Henle. The permeability changes. This ascending limb is permeable to sodium, but totally impermeable to water. So what can actually stay inside? Water is staying inside. Water is staying inside. What can actually go out? Sodium. This goes out with the help of sodium, potassium, 2-chloride co-transporter. Sodium is going out with the help of sodium, potassium, 2-chloride co-transporter. This ascending loop of Henle is permeable to sodium because of sodium, potassium, 2-chloride co-transporter. Inside water is there accumulating, making this segment to undergo dilution. That is why the ascending limb is called as dilution segment of nephron. Descending loop of Henle, concentrating segment. Ascending loop of Henle, diluting segment. Most important points, descending loop of Henle is permeable to water, impermeable to sodium. Ascending loop of Henle is permeable to sodium, but impermeable to water. Ascending limb is permeable to sodium because of sodium, potassium, 2-chloride co-transporter. They are actually blocked by our loop diuretics furosemide. They are also undergoing mutation in a very important clinical syndrome, Bartter syndrome. Very important clinical condition. Sodium, potassium, 2-chloride co-transporter. Its blocker is furosemide. It can be mutated in this clinical syndrome, Bartter syndrome. Very important concept. Surrounding this loop of Henle will be a very important blood vessel. We call them as vasa recta. This vasa recta is considered to be countercurrent exchanger. Countercurrent exchanger is this blood vessel vasa recta. Very important. Ascending loop of Henle is permeable to sodium because of the presence of sodium, potassium, 2-chloride co-transporter. This descending segment is the concentrating segment. This ascending segment is the dilution segment. Very important part, loop of Henle. Alright guys, from loop of Henle, now the fluid will move into distal convoluted tubule DCT, which is very important for sodium chloride reabsorption, calcium reabsorption. DCT, very important for sodium chloride reabsorption, calcium reabsorption. This calcium reabsorption here is actually enhanced by parathormone and vitamin D. Sodium chloride reabsorption, calcium reabsorption. Calcium reabsorption in DCT is enhanced by parathormone and vitamin D. For sodium chloride reabsorption, we have a sodium chloride co-transporter, which is actually blocked by our thiazide group of diuretics that act in DCT. Mutation here in the sodium chloride co-transporter can lead to a very important syndrome, and that syndrome is Dittelmann's syndrome. Very important. DCT for sodium chloride reabsorption, calcium reabsorption. Very important, calcium reabsorption. Sodium chloride thiazide diuretics, sodium chloride co-transporter. Coming near its own glomerulus, they form a specialized association in the form of an apparatus we call juxtaglomerular apparatus, which is shown to have three important cells. The first cell is called as juxtaglomerular cells, which is actually shown to be found in the walls of afferent arteriole. JG cells in the walls of afferent arteriole. Then we have the second cell macula, very important, and one are the glomerule cells. What are their functions, sir? JG cells contain lot of granules inside, thereby they are called as granular cells. I told you they are found in the walls of afferent arteriole. They are mainly renin producing. which is a component of a very important system, renin-angiotensin-aldosterone system, whose primary function is to increase sodium reabsorption, increase water reabsorption. This system. Renin producing cells or JG cells. They are the components of renin-angiotensin-aldosterone system. Then we have the sensor for GFR, asked many times before, macula tensor. Why it is called a sensor? Because whenever it senses increase in GFR, it releases an important mediator, adenosine. This adenosine is going to cause constriction of afferent arteriole. A for A. Adenosine constricts afferent arteriole. The effect is decrease in GFR. So increase in GFR is followed by a decrease. This feedback is called TBF. This feedback. So apparatus. Now, from DCT, eventually the fluid will finally move into our collecting duct. See these. Collecting duct is totally about 2. Simple mnemonic 2. What is 2 here, sir? First and foremost, there are 2 parts of collecting duct. Cortical collecting, medullary collecting. There are 2 important cells you see here, principal cells and intercollected cell. Site of action of 2 important hormones, aldosterone and vasopressin. Particularly on the principal cells. What are the action of these 2 important hormones? Principal cells, ADH. Aldosterone is going to cause potassium excretion. Sodium reabsorption with the help of ENaC, potassium excretion thrown into lumen aldosterone with the help of renal outer medullary potassium channels. Renal outer medullary potassium channels for potassium excretion. Our vasopressin with the help of V2 receptor. Vasopressin with the help of V2 receptor helps in water reabsorption by upregulating this important channel protein aquaporins. Vasopressin for water reabsorption uses aquaporins. So aldosterone, sodium reabsorption, potassium excretion. Vasopressin with the help of aquaporins helps in water reabsorption. So this vasopressin is very, very important. I told you one receptor V2. There are other receptors also. It is called as vasopressin, which means vasoconstrictor. It is the V1 receptor action, vasoconstriction. Just now we have discussed V2 receptor is for water reabsorption using aquaporin 2. V2, aquaporin 2. This V2 receptor blocker, the drug is called as conivaptan. We have something called as vaptans. They are the vasopressin receptor blockers useful in treatment of CR, syndrome of inappropriate ADH secretion. Then we have the recently discovered V3 receptor, which is found in the anterior pituitary that helps in release of ACTH. This vasopressin receptors V1, V2, V3, very important. Please revise their functions. And finally, following all these processes, whichever that is left out need to be excreted in the form of urine. For that excretion micturition, we need to understand about this. Facilitates micturition by causing contraction of detrusor muscle and relaxation of internal urethra. Got least role in micturition. Its main role is to carry pain signals from bladder. Least role as far as micturition is concerned, its major function is to carry pain signals if at all that is coming from bladder. Then we have a somatic supply that is mainly through pudendal nerve, which exclusively goes to the external urethral sphincter. Somatic supply, pudendal nerve going to external urethral sphincter. And finally, we have higher centers regulating our micturition. We have facilitatory centers in pons and also in posterior hypothalamus. They facilitate micturition. Pons, posterior hypothalamus. Inhibitory center for micturition is found in midbrain. You also have a cortical level control at the level of para. Micturition is in midbrain. The highest most order cortex, we have paracentral lobule, which is supplied by anterior cerebral artery. This bladder innervation is very important. Parasympathetic always facilitates micturition. Alright guys, now the bladder filling, its volume changes and the pressure changes. Inside the bladder, volume changes and the pressure changes. They can be studied with the help of this important graph. We call this as cystometrograph. X-axis is volume, Y-axis is pressure. Let's put volume 100 ml, 400 ml, what they actually mean, let's find out. This cystometrogram has got 3 important segments, 1A, 1B and 2. What is happening in 1A? Look very carefully. Volume is increasing, bladder starts filling, pressure shows increase. What about 1B, sir? We are clearly seeing in this 1B, volume is increasing. Yes, sir, volume is increasing, but the pressure is maintained constant. This is the classical difference. In 1B, volume is increasing, but pressure is maintained constant. This is a manifestation of Laplace's law. Even though the volume is increasing, this segment 2, there is tremendous rise in pressure. We are clearly seeing there is tremendous rise in pressure, eventually leading to micturition. What was the MCQ recently asked? This is segment 1B is a manifestation of Laplace's law. They will ask you, first urge to void. This happens if the volume of urine is 150 ml. Marked sense of bladder fullness. If you sit in the AC room for a long period of time, you all have that feeling, the marked sense of bladder filling. That is 400 ml. That is why in this 400 ml, there is tremendous rise in pressure, eventually leading to micturition. So first urge to void 150 ml, marked sense of bladder fullness, we experience at 400 ml of urine. The segment 1B is a manifestation of Laplace law. Below 6.9 are not compatible with life, death is inevitable. Above 7.8, below 6.9. What is the need? Why you need to maintain pH critically? The answer is very simple. Because enzymatic activity and protein structure are very sensitive to pH. Remember guys, very critical enzymes. They may undergo denaturation. Protein enzymes, pH changes can denaturate them. Not only that, our most important central nervous system, if it is acidosis, that is low pH, CNS becomes less excitable. In alkalosis, remember alkalosis is always hyperexcitability. That is why high pH alkalosis, there is hyperexcitability leading to muscle twitches. So enzymes can be affected, central nervous system can be affected. How to critically keep this H plus ion concentration in check? We have three important control systems. First is the buffer control system, chemical acid based buffer system. They act very fast within seconds. They are the first line of control system. Then we have the lung respiratory system. They act in minutes. Buffer in seconds, lung in minutes. They are the second line. Eventually, long term, very slow acting is our kidneys. They are the third line of defense. What they do? First, let's find out the buffers. Important buffer names they will ask you. Which is the most important buffer of extracellular fluid? Any guess? The answer is bicarbonate buffer. Very important buffer in kidneys, tubular fluid, and also intracellular fluid. The answer is phosphate. Bicarbonate, extracellular. Phosphate mainly in the urine and intracellular. Which is the most plentiful intracellular buffer? Inside intracellular, most plentiful. Most plentiful intracellular buffers are protein buffers. Asked many times before. ECF, bicarbonate. Intracellular fluid and tubular fluid, phosphate. Most plentiful intracellular buffers, protein buffers. Next, second line of defense, lung. Lung can do two important things. Remember guys, hyperventilation, hypoventilation when they are needed. And increasing ventilation, hyperventilation, CO2 washout. CO2 washout means this can reduce H plus ions. This can be done for acidosis. Acidosis means rising H plus ions. How to remove those excess H plus ions? Hyperventilation, carbon dioxide washout, H plus levels will fall. On the other hand, hypoventilation, CO2 retention. This can help in H plus ions increasing, mainly needed during alkalosis. So states like acidosis, you will see hyperventilation for CO2 washout. In states like alkalosis, you see hypoventilation, carbon dioxide retention, and increasing H plus ions. So lung helps in both ways. Either it do hyperventilation or hypoventilation, depending upon the derangement in pH. Hyperventilation or hypoventilation. Now finally we have kidneys, the third line of control system, exclusively targeting bicarbonate ions. It helps in reabsorption of bicarbonate. I told you 80% bicarbonate reabsorption in the PCT. Not only that, it also helps in forming new bicarbonate ions, using thereby getting new bicarbonates to the system. And also a special type of cell, intercalated cell. We have two important types. Type A intercalated cell is acid excreting, H plus excreting. Type B is base excreting, which means bicarbonate excreting. There are two important intercalated cells. Acid excreting is type A. Base excreting, bicarbonate excreting is type B. Depending on the situation, whichever needed, they can be upregulated. Type A intercalated is acid excreting. Type B intercalated is base excreting. Then we have a very important concept of anion gap, which simply means these are those anions which are actually present, but we are not determining them in laboratory routinely. It is mainly due to our plasma protein anions, sulfate and phosphate. They can ask you a calculation-based question. How to calculate this anion gap? Sodium minus bicarbonate plus chloride. So 140 minus 25 plus 105. Usually it is 10 milliequivalents per liter. This anion gap calculation helps in differentiating metabolic acidosis as normal anion gap metabolic acidosis and high anion gap metabolic acidosis. To differentiate normal anion gap NAGMA and high anion gap HAGMA, you need to calculate this anion gap. This is the formula. We are clearly seeing the normal anion gap value is around 10 milliequivalents per liter. What is the formula? Sodium minus bicarbonate plus chloride. The normal value is 10 milliequivalents per liter. Very important area guys, renal physiology and acid-base balance. Please to revise them. Thank you so much.